Good day, everyone, and welcome. I'm Jack Van Horn from the University of Virginia. Please allow me to welcome you to our 2020-2021 Foundations of Biomedical Data Science Seminar Series. Working previously with colleagues through the NIH's Big Data to Knowledge program, we began this seminar several years ago with the goal of providing a foundational resource for the theory, practice, and applications of data science in biomedical research. Now based at the University of Virginia, we are now continuing this seminar series with a focus on the data science and its particular applications in thematic biomedical topic areas. The theme for this year is the brain and the data science necessary to process, analyze, model, integrate, and interpret brain form, function, and connectivity across scales in health and in disease. The variety and richness and scale of neurobiological data types increasingly necessitates novel data science methods. Advancing data processing, data mining, statistical analysis, and synthesis and visualization are all needed to make progress in the neurosciences to characterize, complete, and come up with more comprehensive neurobiological systems. These will be important for the identifying the most efficacious treatments for development, neuropsychological and neuropsychiatric diseases, as well as syndromes which affect the brain as we age. Over the coming weeks, we'll present a blend of lectures on the basics of data science, brain science, and their intersection. These videos are being streamed live via YouTube, are also being recorded, and will take their place in a corpus of foundational video content concerning data science applications in biomedical sciences. Please share the YouTube channel link with your colleagues, your students, and other interested stakeholders. In beginning this year's seminar series, I'm pleased to welcome Professor Don Brown from the School of Data Science at the University of Virginia, who will present his appropriately entitled lecture, How to Do Data Science. Donald Brown is the founding director of the Data Science Institute at the University of Virginia, the co-director of the Integrated Translational Health Research Institute of Virginia, iTHRIV, and the Quantitative Foundation Distinguished Professor and Professor of Data Science here at the University of Virginia, which is the first such school of its kind in the United States focused on the subject of data science. Dr. Brown is a fellow of the IEEE and recipient of the IEEE Joseph Wohl Career Achievement Award for his work in systems engineering and data fusion. He conducts research in predictive technology, data integration, machine learning, and simulation optimization with applications to health science, security, and to safety. Our Innovation Lab participants should be able to submit questions for Dr. Brown via their Zoom chat feature. I will synthesize these and present them to Dr. Brown for discussion during the last 10 minutes or so of the seminar. With that, welcome, Don. We are very much looking forward to your lecture.
Well, thank you very much, Jack. I appreciate that very nice introduction. So I'm going to jump right into it as to how to do data science. And I'm going to start with telling you a little bit about the School of Data Science at the University of Virginia, because that gives a background of what we're going to be talking about. We call it a school without walls and a comprehensive university. And by that, we mean that we reach out. We're not like a lot of data science programs that come out of a single department. For instance, a statistics or computer science department, nor are we one that come out of the joining of two departments or within a single school. We are, in fact, a school that exists on its own, and it reaches out to all schools at the university. And we have another 11 schools at UVA that we reach out to. And in doing so, we try and leverage the research and scholarship of those other schools that we have at UVA in order to create a set of data science programs and to conduct research in data science. We've been advised by business, government, and academic partners, and that's what's given us a sense of what data science should be in the world that expands these areas, business, government, and academic institutions. We also coordinate a lot of all of the teaching in data science across these disciplines, across programs throughout the university. And we've created new educational programs, particularly the master's program, but we now have a PhD program that's under review, and we have an undergraduate program that we'll be rolling out soon as well as an undergraduate minor that is already in place. We also enhance the hardware and software infrastructure that supports data science. Okay, so let's start out with a little question about what is data science. And it started out with the idea of what is big data. And when there was this great joke that big data is like teenage sex, everyone talks about it. Nobody really knows how to do it. Everyone thinks everyone else is doing it. So everyone claims they are doing it. And this is sort of the underlying joke behind the area, but that Dan Ariely had. It's a very nice little way to think about what we're about in a lot of institutions. But to get more serious, what is data science? Well, actually, data science has been a field or a topic of discussion in academia and in business and in government for a long time. Well, at least since the 1960s. It's been definitely in papers that people have talked about data science. In 1998, Wohl gave a very interesting talk in Michigan where he said that really data science is statistics. But since then, and frankly, even then, most people didn't believe that. And in fact, they felt that it's quite different. It's an area in and of itself. But what is that area in and of itself? Well, let's take a look at some things that others have written about what data science is. A concept to unify statistics, data analysis, machine learning, domain knowledge, related methods in order to understand and analyze actual phenomena. And this is what Hayashi said also in 98. And then you've got this one from Leek. The key word is data science, not data. It is science. Data science is only useful when the data are used to answer a question. And then we have Dar, who wrote that data science is a study of the generalizable extraction of knowledge from data. And Lowe, who said data science is a multidisciplinary blend of data inference, algorithm development, and technology in order to solve analytically complex problems. Now, I could give you more and more of these things, but I guess the point I'd like to make is that there are two central concepts that come out of just reading all but Wu's initial comment. There are two things that sort of run through all of these definitions. And as I say, there are many more I could give you that these two concepts also appear in. Think for a moment and see if you can and see what those two concepts are. And if you have them, write them in the chat, and I'll try and take them as input to this. But think about what those two areas are. And I guess as you're thinking about it, notice that we have in a lot of them this unifying of multiple areas, okay? Blend of data inference, algorithm development, technology. So this idea of integration of fields, interdisciplinarity, runs along a lot of the ideas of what data science is. And the other thing that runs into it, a lot of them, is this idea of analyzing actual phenomena, answer a question, okay? Solve an analytically complex problem. These are the two things that we're going to focus on because those that we consider to be at the heart of what data science is. So let's take the first one. Data science combines disciplines. There are a lot of sort of these Venn diagrams of data science that try and capture this idea that data science is an interdisciplinary activity. I've given you one of the very simplest of these, and there are a lot that are very complicated, some of them that are quite funny, but the basic ideas is that data science seems to be about bringing together a number of areas in order to answer a question. And there's another version of it. We like to say data science is a team sport. So you can think about all these different areas, all these interdisciplinary areas coming together around the idea of trying to solve a data science question. And that's at the heart of a lot of what we think about in data science, is this notion of bringing together these different fields in order to solve the problem. And the other aspect, as I say, is the solving of a problem. We need to solve a problem. So it's, again, one version of it is it's extracting knowledge in order to do this, okay, in order to solve a problem. But fundamentally then, once you understand, okay, it's great, it's this interdisciplinary approach and it's focused on a particular problem. This is a very application-oriented field. The question then is, how do you do it? How do you go about doing this? And I love this quote from Tukey because it really gets at the frustration. He pointed out the combination of some data and an aching desire for an answer does not ensure that a reasonable answer can be extracted from a given body of data. So just because you've got the data and boy, you really want to solve the problem and you've got all these different fields, doesn't necessarily mean you're going to get an answer, and you're going to get the answer that you're looking for in particular, but that you're going to be able to solve it. You got to have something else, and that something else is you need to have an approach. You need to have a structured way to go about the problem in order to get an answer, and that's what we're going to talk about throughout this talk is how do we go about doing that? Well, one of the earliest ways that people presented for doing data science was what was called the cross-industry process for data mining, or CRISP-DM. And it represents this process flow. It says you start out with some sort of a business, because this was a business-oriented group that came up with this idea. They were looking at it as a business understanding, but you could think about this in general. You could think about this as the understanding the health sciences application that you're working on. Data understanding, you're trying to understand what the data have in it, then you do the preparation, the wrangling, all that kind of stuff. Then you do the analytics or the modeling, the evaluation of your results, and then you communicate your results through deployment. And this method really does describe a lot of what it is that we're about when we think about data science. But we were somewhat dissatisfied with it because it implies a process flow that doesn't really get at the way that a lot of us work on data science problems. And one of the key insights came from a colleague of mine when we were looking, and we looked at probably 15 or 20 of these things. And then I'll give him credit. He noticed the idea that you could actually fold them one on top of the other. So in fact, you could bring this data understanding, business understanding. You could look at this as one area. You could look at data understanding and deployment. You could fold them back on each other. Data preparation as well. Bottom line is that we came up with a different way to think about it that we think really captures more about what data science is about. And we call this the 4+1 model. And the 4+1 model is the four major areas. And these four areas are value, design, analytics, and systems. These are the four areas that we consider to be the critical parts of data science and operation. And at the center of it is this notion that I said is critical in data science. You're solving a problem, and we call that practice. You're solving a problem for some real application. You're trying to answer a question. And that's the bullseye in this notion. That's the +1. That's where we're looking. It's in the middle because it's the key focus for all areas that we're working on. The four areas represent the four key aspects of data science, and then the center point represents what we really want to keep in mind at all points. So it intersects with everything that we're trying to solve a problem for some organization in the real world. Now I'm going to talk about those intersection points, and you can see you've got concrete, human, abstract. I'm going to postpone talking about those for a little bit and go into some of the four areas here. So that we have a better definition. And the first one we think about is value. And what value does is it represents this combination of both ethics and business planning. It's bringing together, and again, you can replace business with organizational planning or organizational understanding. What is it that we're after? What is the problem that we're having to deal with? And how does that relate to the organization? How does it provide value to that organization? How is it moving that organization forward in some way? And at the same time, what are the ethics? What are the values as they relate to the ethical concerns around the problem that you're dealing with? And there typically are those. And every problem that we deal with, we come up with these kind of issues, and we need to deal with them up front and center in doing data science. And there are these other points. There's policy making, organizational motivation. All these things are part of this value component. A key part of the value step, if you will, of the value aspect of data science is the formation of what we call the value proposition, where we describe specifically what value this or values this particular work is going to bring to the world and to the organization for whom it's done. The one nice thing about this 4+1 model is that we expose tensions, and tensions are good. Tensions tell us that these are the values, or these are the trade-offs that we've got when we're working in this space, because you can't work in a space like data science without experiencing trade-offs. There are always going to be trade-offs in the way that you perform this work. If you expose them and make them explicit, then you can deal with them in a much more effective way. And clearly we have these tensions here. We have enterprise versus ethical values. Another way, private interest versus public good. The organization has issues, it has values, it has things that it wants to accomplish, but at the same time, we have to think about the larger values that we have to society, or the values that we have to individuals that for whom we're working with in order to accomplish the data science project. And we have to think about these larger societal values whenever we do a data science project, as well as the organizational values for the organization that we're working for. Okay, design, the next component of this 4+1 model. Design is the human-centered part of this. This is where we really think about the human being interacting with the data science piece. This is where you really look at what the data is. As a data scientist or data analyst, you're trying to understand the data. You're the human trying to understand what it is that you're dealing with. But it also deals with your customers, your stakeholders, everybody that you're interacting with. The design component is all about this human interaction with the data, with the technologies, with the products of the technologies, with the products of the data science work. All of that is what's involved. And the little picture that I'm showing you is this typical way that we think about design is it's actually giving us ways to visualize a lot of, visualization is a key part of design. How do we visualize the data? How do we visualize the structures that we're dealing with? And as a data scientist, we want to understand the data, and visualization is one very powerful way to do it. But as consumers of data science projects, our customers, our clients, our sponsors, they want to visualize. Visualization is a good way to see what it is that you've accomplished. And in the examples I'm going to give in this talk, I'll try to describe some of those. Some key activities then in this area are representation and communication through database design, the curation of data, as I say, the visualization of complex data, okay, the display and visualization, and visualization of the analytical results, the showing of those results. Tables we use a lot, but we also use visualizations. Tensions, discovery versus product. This is a major tension. User-facing versus analyst-facing. Another tension. Is it something that the analyst understands and gets, but the user has no clue, the sponsor, the clients, they've got no clue what you're talking about. These kind of tensions exist within the design component. And they're things that we're aware of. Once we make them explicit and we're aware of them, we can take actions and deal with them. Okay, the systems framework is part of the data science. I say this, that the first two, value, I think people think about, but they don't necessarily think about it the way that we've structured in terms of this, both the value to the organization and the value to society and the value to the individuals that we're working with. And design, frankly, a lot of people don't really call out as a separate and equal component to these other areas. The next two, this one in particular, systems and the analytics piece, people think of all the time when they think of data science. These are the ones that most people, frankly, firmly associate with data science. The systems area is the area where we think about the computation. This is the infrastructure that provides the support for working with the data that we're working, the data that we need to solve our problems. It includes not only the structure, the underlying hardware, but it includes the software as well, in particular, the pipelines to move the data to where they need to be moved in order to get the job done for us. We think of it as computational science and technology, necessarily opposed to computer science. And the key activities here are really developing this infrastructure, this performant infrastructure that that can accomplish what we need to do. And we think about cloud resources. This is the name of the game today, but it involves a lot of other things as well. And some of those are mentioned here, including the networks, the resilient pieces of the network and the underlying infrastructure. And as I said, also the software involved in accomplishing this. The tensions here, we have development versus production, because a lot of times there's tremendous pressure to get production systems out, as opposed to really spending the time that's needed in order to build the resiliency that we need and maintainability in these systems. Volume versus speed, another major area of tension. Extensible versus immediate. These are the kind of tensions, again, explicitly making everybody aware that we've got these tensions as we go through it. Analytics, when people think of data science, they completely associate analytics with data science. And it is a very key element. This is one of the major, the two major things that I think have made data science what it is, frankly, are this one and the one that I just talked about. We now have the hardware systems that allow us to accomplish tasks that were frankly impossible before. And we have the analytical methods. We've produced the methodologies today that can actually go after incredibly difficult problems. So these two together have really elevated data science to a major field and made us what we are in terms of the things that we can accomplish with the field. So I spend a moment here on analytics. These are the mathematical machine learning kinds of things that we think about when we think about data science. And it involves all these things. There's a long list, and I've only listed a few here: optimization, signal processing, neural networks, and I've got a picture of a deep learning network on the right. These are the kinds of things that you think of when you think of the analytics, but it incorporates all aspects of this. We are bringing together the broad swath of analytical capabilities that have been built up and continue to be built. I mean, it's an ongoing area. It's wonderful to watch and wonderful to be part of, to watch what's happening in this area and the tremendous methodologies, wonderful methodologies that are being produced on almost a daily basis. Key activities here is obviously converting. This is where the rubber meets the road. Taking the data and turning it into something that's useful, turning it into the answers to the questions that we've posed. This is where it actually gets done, is in this analytical part of the data science structure that we described, the 4+1 model. So this is where we're really meeting the challenge that we've got. The tensions here, there are many of them. Again, I'm mentioning just a few. One of the big ones that people talk about a lot is causality versus correlation. And whether we need causality or whether we can be satisfied with correlation. Is correlation sufficient for us? Do we really need to drive to causality? Do we need to understand that? Inference versus prediction, another one that's spun out. Prediction has been the new major evaluation methodology that we see in data science, but we continue to rely on inferential methods. Observation versus experiments. Feature selection versus feature engineering. How do we pick and understand the contributors, the predictive variables that are contributing to the answers that we're seeing? And accuracy versus interpretability. A lot of problems, we can produce incredibly accurate results, but we've got no clue. We've done it through black boxes that we don't understand and that we can't explain very well. So these are all issues. These are tensions that we have in the analytics area. Okay, and the last, as I say, the bullseye in this whole process is practice. This is where the problem is. And practice is what brings everybody together. It makes it the team science. Okay, this is characterized by everybody working together. You got domain experts, people who really understand at a deep level what the problem domain is. And they can help when working with the people who are deep into the data science methodology, understand how to go after the particular problem that you're going for. And so you work together in order to produce these kinds of the solutions that are actually going to be true solutions and not just theoretical solutions or solutions that get written up in a paper and never read or not used, but actually translational solutions that make a difference and actually help an organization advance. Okay, key activities. Contact with domain knowledge and real world problems. This is, it's all about actually digging in and understanding what it is that you've got in the area that you're working. What you've got at the level of knowledge and what you've got at the level of data and what you've got at the level of people who understand the characteristics of those. Tensions, goals versus resources. This tension just exists in every problem-solving domain. You've got a lot of ambition, but do you have the resources to go after it? And can you bring the kind of teams together with the resources the teams need in order to solve these problems? Integration versus decomposition. Typically, you've got analytics versus synthesis, and this is always these kinds of things play out in many real problems. And data science versus practical understanding. When I teach data science, I try and get my data science students to understand that when they work in an area, they can't expect that their subject matter experts in that area are going to do everything. They've got to learn that domain. They've got to get in and understand it well enough that they can communicate in a professional way with their data science, with their colleagues who are steeped in that domain, and they've got to understand it so that they're asking the kind of questions and working with them in a way that's effective. And this is a tension that exists in almost every team that goes after these data science problems. Okay, so let me summarize a little bit about this 4+1 model and say with a couple of key points here. First one is that this is not unlike these process models that people have thought of in terms of doing data science. This 4+1 model is not a linear model, but we typically start with value, okay? So it isn't like you go from value to design to analytics to systems. It's that we don't think about it that way, but we do say that you start with value. There's virtually, I can't think of any problem, but I'm not going to say never, because it's possible that you could think of a problem that doesn't start with value, but every problem that I've worked in starts with value. That value component is absolutely key. You want to understand the problem from the perspective of the organization. What is it that they want to accomplish? What are their goals? What are their objectives? But also, what are the ethical issues? What are the societal issues that impact upon those goals and objectives? And how do they influence the way that you're going to conduct data science and the way you should think about it? Okay, another point is the way that we try to draw this is visually to give you the sense that practice intersects with everything, okay? It's absolutely important that whatever you do, you're always thinking about the problem. It isn't, again, the problem we have with those process models is, frankly, they give the impression that you do that, what we're calling the value step, the value proposition kind of piece. You do that, you get it done, and then you forget about it and move on to the next piece. That's not the way it's done here. This is an intersection with practice, and this intersection with practice means that you have to think about that what you discover in that value component as it impacts on the question you have in the practical area carries through in everything you do. And your impact, and you're constantly working with people who are experts in the domain to understand the data science piece as you go through it. And if you happen to be an expert in this, in whatever domain, which I think most of you probably are, you then are actually, you're intersecting at the value design and analytics and systems area as well. You're kind of coming from the middle out, and you're saying, okay, I'm going to do these pieces. And that's great. And that's the kind of thing we want you to think about, is that practice intersects with everything. The emphasis is not always the same here. Some problems are going to emphasize analytics more. Some problems are going to emphasize design. There's some problems, frankly, they don't care about analytics very much. They care about the visualizations. They care about the communications aspects, which means they're very, very focused on design. And so, and that's fine. It isn't that each one of these things has to get equal emphasis in every problem. They're going to be problem dependent. So don't think that this suggests just, I mean, again, we draw it this way to emphasize that we consider them all equal parts in doing data science, but they're not necessarily all equal in doing a data science problem. Okay, the meaning of the boundaries. These things all have interesting boundaries, and frankly, I could talk about this 4+1 model and all the interesting pieces of it. But I'm just going to point out, and I'd like you to think about it, that when you look, for instance, at the intersection between, or at the boundary, I'll say, between value and design, it's a human boundary, because both of them are very concerned about talking to people. The interaction is with people more than it is with, I'd say, analytics or with machines or things that are solid in the world. This is about people talking to people, is what that intersection is about. Both of those areas are very much concerned about this human interaction, that's key to data science. On the other hand, if you look at the opposite side, systems and analytics, they're intersecting with the machine. They're very much focused on what's the hardware and the software that's on that hardware going to do for me. They're very focused on looking at the capabilities of those machines and how they're going to accomplish their tasks. Again, I'm using machine, but machine, I mean that as well in the software parts that's on those machines. The boundary between systems and value is concrete. You want to make it very, very precise and understandable, and it's concrete in the sense of language and communication between them. In terms of design and analytics, it's abstract. We write, a lot of it is mathematical, a lot of it is pictures and graphs or displays. These kinds of things exist between these areas. And so these boundaries make they provide a little bit of meaning of where these four areas overlap with each other and share commonness between their activities. Okay, one thing that the 4+1 model does is it provides a way, as all process models do, but the 4+1 again is not strictly a process model, but it does provide what process models do, which is a notion of completeness and coverage. Have you done what you need to do in order to get the data science question answered? And that's what this kind of approach does for you. It allows you to make sure that you've really done due diligence there. Okay, I'm going to turn now to a couple of examples. I've talked at the high level of what the 4+1 model is and how to do data science with it. And I'm going to give you a couple of examples now as to how this is done. I don't work in neuroscience or in the science of brain, but I have several health science examples that I've worked on, and I'm going to describe those as examples of this. One of them is environmental enteropathy, which has to do with children, and the other one is adverse surgical outcomes. Okay, environmental enteropathy. Environmental enteropathy is a relatively newly classified disease. It's only been classified in the last 4 years. It's a subclinical inflammatory disease of the intestine. And if you look at the right, you can see this notion of what's happening here. You can see that normally we have on the left, we have a healthy representation where we've got lots of surface area that basically can absorb the nutrients that are coming through. And on the right, we have a non-healthy situation where we have decreased electrolyte absorption, we have decreased absorption generally. So this kind of, the villi on the left are healthy, they're able, and this is this very, very nice design that we have, which allows us in a very small space to have a very, very large surface area for this absorption. And unfortunately, in the right-hand side, because of a number of environmental conditions, it becomes diseased and unable to absorb. So this kind of condition is associated with malabsorption, linear faltering, and stunting. Children with it are stunted. Impaired cognitive development, reduced responsiveness to nutritional intervention as well. So nutritional intervention, of course, is the first point that we take, and these children frequently don't respond well or at all to it. And also they don't respond to immunogenicity and vaccination, oral vaccination as well. Okay, what's the value? The value piece of this is really very clear. Half the global deaths in children under 5 years are attributable to undernutrition. And thus the study of this is of tremendous value. It's a worldwide value to really understand what's happening here, not only to the individual countries, but also the world. We need to understand it. We need to treat this. And you can see that it is something that's not focused just in one area, but it's focused in a number of areas throughout the world. It's an important concern. The ethical issues here clearly, as in all health issues, we need to think about the privacy and protection of the patients that we're dealing with. And we also need to think about, in this particular case, research collaborations that are truly collaborations and that are not dominated, as has happened, unfortunately, where some countries, and I'll say our country, comes in and tries to say, this is the way you should do things. This is a collaborative effort. It's a collaborative effort with the countries in which we're working in order to accomplish these tasks. And these kinds of collaborative efforts are incredibly important in order to make these solutions lasting and effective. You can do all the great data analysis you want, but if you don't create the kind of collaborative infrastructure at the research level and at the translational level for getting these solutions implemented, then it's all for naught. So it's incredibly important for us to have these collaborations and to understand how to create those collaborations at the beginning. Okay, design. We've got, in this particular case, we had 100, this is one example, we've got a lot of these things, but give one example here. We had 108 de-identified biopsies, and they came from a number of different diseases, celiac, environmental enteropathy, and normals, okay, or controls. And the way that we do this is that we cut up the image as it's shown, and we do this in order that we can deal with the fact that it's a very high resolution image. Okay, yeah, you can see celiac and normal biopsies were photographs, EE biopsies were digitized slides. Data were augmented by a factor of 30 via rotation, horizontal and vertical, and I show that in the bottom there. So you can see we can rotate these things in order to increase the number of data elements that we have to work with in our models. The patches then are from whole slide images. So we're gonna cut it up. We're gonna grid this thing, and we're gonna look at patches from the whole slide image, because we can't. Our analytics can't deal with the whole slide, but we can deal with patches from the whole slide. I'm going to mention this color balancing in a minute, but that's a result of the staining, and it's a big deal for us in order to work on this problem. Okay, so the pre-processing, as I say, we first we grid the image, and after doing that, we create these patches, and some of those patches are absolutely worthless because they're taking pictures of nothing or very almost nothing. And so we run that through a process. In this case, it's what's called an autoencoder, in order to do a clustering and find the areas in the patches that are actually worth using for our modeling approach. And this is a key part of this design piece, is understanding that. I mentioned the staining, hematoxylin and eosin staining, H&E staining. This produces different colors based upon the characteristics of the underlying tissue, and but unfortunately, those colors also depend on local conditions in the labs, and that creates a bias. And in our particular case, for example, we had only the normals we got from a number of places, including the United States, but we have no environmental enteropathy cases from the United States. So there's a natural bias that can occur, because what we're doing when we're doing the modeling is just finding a color difference represented by the staining, and not any real difference that exists in the underlying tissue, and that's a problem. So we need to deal with that as part of design. And this is what's called color balancing. It seeks to convert all these images to the same normalized color space, so that we don't have any bias as a result of that. The analytics that we use convolutional neural nets, and I've got a picture there. I'm not going to go into the details. This isn't the talk to go into the details of convolutional neural nets, but That's what we do. These are the latest techniques for going after these kind of images. These are what's called a deep learning architecture, and we can employ it for this hierarchical image classification problem. These layers are called feature maps. We can stack them together. We can do all sorts of cool things in order to go after this. And the output then is actually a probability of classification into one of these disease categories. From the system standpoint, I'll just say that we create pipelines to process the data. We use the cluster systems or clusters of computers. We also used graphical processing units or GPUs. These are the latest, or these are things that have been around for a while for really the gaming industry, but they're exploited by us because they work very well on these for these deep learning problems, and they allow us to really find where the knee of the curve is when we're trying to calibrate our models. So building an infrastructure, a systems infrastructure that has those capabilities is very important to us. Okay, at the other end, when we get the results, we have a design piece as well. We have to show people the results. And the first table here shows the results that we get when we train on one color balancing approach and test on that same color balancing approach. And you can see that we get very good results. We're getting good classifications for environmental enteropathy, pretty good for normal, and doing well as well for celiac disease. And we do it as well when we change the color balancing in the test set. You can see that that the approach remains robust to these kinds of things. And that's what we're trying to show is the accuracy here. And the important thing is that we're getting better accuracy than pathologists with environmental enteropathy because it is a new disease, not well understood. And we're getting it's robust to this color balancing problem that we mentioned with the H&E staining. And that's the kind of result that we like to see in these approaches. Okay, I'm going to then shift to another example problem to show you this 4+1 model. And this one is adverse surgical outcomes, and the outcome we're going to look at is AKI, the sudden inability of the kidney to clean the blood of toxins. And you can see that it occurs in the United States with not an insignificant amount of cases, 25,000 per year. And I don't have a date there, but I think that was 16 is when that last was recorded. Okay, 24 to 48 hours to diagnose using current methods. You've got to say that this is a potential problem really fast. The mortality rate increases as a result, requiring hospital 5 times during hospitalization. So it's got to be diagnosed quickly. Current predictive model for this. So what's the value? The value is that the current predictive model really is not very good. It comes out of this model from the Society for Thoracic Surgeons. It uses only preoperative data. It fails to accurately identify at-risk patients, and I'm going to show you that in a little bit here, with sufficient time to prevent injury. The goal then, the value here is then to provide more accurate prediction of AKI for earlier intervention. So what you want is you really want to do a number of things. You want to say something about creatine change. You want to say something about rifle categories, which is no classification, risk, injury, failure, or loss. These are the ways that it's currently thought about in that current model. And the ethics of this are around the need, again, to protect personal information. And this is a classic problem we have in the health area, that we may have we may have something that is misrepresenting the underlying population in many ways. Our patient population may not be representative of the general population we're dealing with. We may build models that are basically only effective for certain classes of patients. And we need to think about this. We need to think about the stratification of our patient population as we go into these. Okay, the systems area, we've got a variety of machines that we can use on it. We've got large clusters. Again, we've got GPUs. We need to do this rapidly and provide the results in the operating room if possible. There are 3 major areas that we were looking at: creatine change, rifle categories, no class which says, hey, look, do something now, or don't worry, it's okay. And the approaches that we are using, again, there's a laundry list of techniques that we applied to these kind of problems, and they're listed on the right. These are analytical solutions that come out of this whole bag of tricks in the analysis area that have been built up in the last 20 or so plus years to go after these sorts of problems. And all of them were applied here in order to try and understand what it is that we were dealing with, and could we in fact solve these different problems. The design. Sadly, we only had 5,000 surgeries in this in the data set that we could work with. But even more sadly, if you look at missing data, extreme values, and mismatches between data sets, we ended up with only 335 that could be used for the analysis. So this is a problem that we find all the time, again, in the health area, that we need to work with. And we also have imbalance. Creatinine changes, just showing you a little bit of that imbalance, that it's imbalanced in certain ways that allows us not to be able to apply these models as effectively without doing other things. We need to reach into our bag of tricks and understand how to go at it. The design, there's a lot of this in the design area here. Then clearly, this is just to tell you that in order to do this problem, a lot of work was spent in order to get the data to the point that we can actually use it very effectively. I'm going to point out only one piece here in the middle, and that's that in order to deal with this missing data and characteristics, we use simulations, okay? We simulated patient characteristics in order to create a more balanced training set that we can actually use for our results. And that's a key part of a lot of, again, health problems. You have to think cleverly about how you can build data that can be used for doing the analytics, and the design places where a lot of that is where that work gets done in order to provide you with the data that you need for the analytics. This is just to show you. I told you that STS baseline, the Society of Thoracic Surgeons baseline, is not very good, and this kind of shows you that result. If you look here, you see that their model basically predicts renal failure for patients. Whoops, sorry. Got to try and use my mouse without flipping through these screens. Okay, so if you look, they're predicting people that had no creatinine change, okay, or very little creatinine change. This is what they're predicting as a result. And all the people that were most affected, okay, all of them were not predicted, okay? So this model is totally ineffective in doing what it needs to do, which again is back to that value of what we're about. In contrast, you can see that the results that were built here do a pretty decent job of doing it. They're predicting pretty well. The predicted results, okay, and the observed results. They're missing some, however, okay? They're missing some down here, but they're doing pretty well at predicting across, again, a small data set, but they're predicting much better than you're getting out of the current system. And that's what we're after. You can look at the rifle categories as well and see once again that the predictions here are quite good compared to what they are with the current system. They're still not great in the sense that they're doing perfectly, but they're doing much better. And in fact, they're tending to overpredict with only a couple cases of underpredicting, with fewer cases of underpredicting, which is again showing improvements on this. The same thing can be done with a binary classification predicting injury and failure. We're seeing this, again, improved performance, again, not perfect performance, but improved performance with these results. We also can find the significant predictors, so we can give the clinicians a sense of where to look in order to understand. Again, these are models that are not black boxes, that we can go in and we can look at characteristics that can help them understand and communicate with them. Again, this is at the design level, communicating with them what it is that they need to look at clinically in order to make these decisions about possible adverse surgical outcomes. Okay, I'm going to summarize then and say data science, as we've seen it, integrates disciplines and technologies to solve problems and extract knowledge from data. So it's all about this interdisciplinary, integrative approach, which is after real problems, important problems. The 4+1 model, as I say, I think we've put together a way to think about data science that helps guide us in when we're doing data science. If we think about these 4 areas as we go into a data science problem, always centered on practice, what the problem is, then we've got a good framework for approaching solving true data science problems. Okay, I think I've got 10 minutes left, as was asked. So I guess I'd like to turn it back over. Jack, I can see the questions, or you can do what you want. Or how would you like to do it, Jack?
Don, firstly, thank you so much for that great overview of data science and why we want to practice this. We do have a couple of questions that are out there. Let me just, before we begin those are a little more technical. Let me just ask you a couple more broader based questions before we begin. I think I know the answer to this, but I wanted to get your impressions about this. Is data science itself an insular discipline? That is, can one do data science for the sake of data science, or is it inherently a multidisciplinary effort?
Data science is inherently a multidisciplinary effort. You really, I mean, in our world, in the world that we're dealing with now, where data science is so important, it has to be multidisciplinary. It has to bring all these characteristics that we've talked about here. You can't be, I mean, don't get me wrong, there are people who can be very specialized, and that's where a lot of, quote, data scientists have been thought to come from, who are very specialized in both the analytics or very specialized in the systems area. But that's not going to do it in a real data science problem. And I hope I've illustrated that. You've got to be someone who can actually do, for instance, not only the analytics, but the design component as well. And your team has to have those pieces on it. If you want to, if the problem is so complex that you need very, very specialized people in analytics, then you've got to have equivalently very specialized people in design to help you put this together. So data science, as we think of practicing it now, is very much this interdisciplinary piece.
Yeah, I think this kind of leads into the second part of that question, which was what sort of attributes are kind of necessary for people who are interested in beginning careers as data scientists?
Oh, wow. Yeah, this is a fun question. And I guess I could throw it back to you as much as but it's I think a guy like you, Jack, is a perfect example. I'll since you were complimentary me in the beginning, I think somebody who is invested in a problem like you were invested in the brain, who's just really looking at it and saying, good gosh, I want to understand these characteristics, and I want to really understand what's happening in this field. And to do that, you're just naturally going to be led to all 4 of those areas by your inquisitiveness about the fundamental question that you're asking. So I think somebody who comes to data science has got to be someone who's inquisitive, curious, and wanting to really make a difference in an area that is important. And as a result, they are going to, by that drive that they have toward solving that, be driven to these 4 areas that I've described, and wanting to understand them so that they can really go after that problem well.
That's great. And one final portion of this before we get into some more technical questions about things is you are the co-director of an NIH CTSA program. And I'm curious, what does data science have to offer the biosciences from the point of view of translational research in terms of education and training?
Oh, in terms of education training, I was going to say, if you stopped before that, I think it's everything. It offers everything to translation. I think you can't do translation without doing data science.
I agree.
But yeah, well, in terms of education, we're trying to provide, I shouldn't say we're trying, we have provided a number of what we call learning shots that are giving you, more deep dives. And there, in fact, we have one that's specifically on this 4+1 model, a colleague of mine did. And then I, for instance, did one on analytics. And so we give deep dives into each of these areas. We go in more depth to describe characteristics of each of these 4 areas. And so that's what we've been trying to do, is to build these learning shots out. And then we have others that are just, again, versions of my talk here today. They're case studies. I gave you 2 quick overview kind of case studies. But I have a colleague, for instance, and she's built one that's on exactly that environmental enteropathy. She's done a full up, 30 or 40 minute presentation on just that, describing data science for that problem, instead of the whatever I spent today, 5 to 10 minutes. I don't know what it was. So it's all of that together that's trying, I think, to give people that are interested in translational health science, give them a sense of how data science is so critical to their mission.
That's great. So some of the questions which are rolling in here, you can take a look at these yourself if you want to see the some of the language here. But in the discussion of the enteropathy was kind of interesting. You kind of mentioned several techniques for each of the outcomes, and how were how are these chosen? And based on predictive power, for example. And another part of this question that somebody else is asking is how is the robustness defined?
Yeah, let me answer your first part, and then I'll try and deal with the second one. So the first thing is that you bear in mind, this is like any talk that you get. I've never been to a conference where you don't get a talk where it appears like they had this incredibly complicated problem, and boy, they were brilliant, had these these techniques and got this great answer, and gosh, wasn't that wonderful. What you're missing is, of course, all the blood, sweat, and tears that went on to try and figure all that out and figure out how this went together, which, and it was all there. Don't get me wrong. I'm not going to pretend. We're, what can I say? We're not Jon Snow. We didn't come up with this brilliant insight. There was a lot of work to try different techniques out here, Jack. You got a bit more of that at that last thing that I gave on the surgical safety, because I put up there the list of things that we were trying, and some of which didn't work very well at all. And that's really the way it was with environmental enteropathy. We tried a bunch of different things. And even to this day, this problem, we're still working on versions of these problems right now. And we continually try stuff. And we're trying newer things. We're trying different versions of things. The nice thing about the world now is that, as I say, we've got a lot of hardware and software that we can just spin up and try quickly and throw it out when it doesn't work. So that's good. The bad thing is that we've got a lot of these things that we can try. So you've got a lot of things to choose from. So it can just frustrate the heck out of you. So you do have to be clever about how you're doing it. And you do have to take I'll say a scientific approach and pick the ones that make the most sense for your particular problem.
Yeah, and somebody else was asking about a little bit about the conditions that one might use to kind of decide whether or not one should use a traditional linear regression or a gradient boosting style approach, or maybe an alternative might be whether or not you're going to use any sort of penalized regression type of approach. What sort of things might you look at in terms of the conditions of the data, or is it just, you should try all these things and find the one that works best?
No, it's more than that, because frankly, it's kind of what I said about this interpretability thing. The one that works best may not be best for your problem domain, because that last one, as I say, it was extremely important for us that the surgeons in this case understood what it was that they could use in order to make these determinations. Because it was important for them to know that, since it isn't a matter of just plugging this in and getting an answer out. They want to basically look at these characteristics of these patients and themselves make a determination. That's frankly why they get paid the big bucks, is they need to make decisions about their patients, and they need to understand what it is that this thing is giving them, this thing being the data science solution that is telling them, hey, this is a probability of this, it's got to give them that answer. I didn't answer the question on robustness. That I gave the robustness thing I mentioned with regard to this color balancing, and that means that it's robust. I can give it different values, different ways in which we've done that color balancing, and it's still going to produce an answer that that is good. It's going to produce a very nice answer. So it's when I say that, I mean it's not sensitive. It's not terribly sensitive. It's sensitive, but it's not strongly sensitive in the sense that the results change dramatically for the worse as a result of doing a different color balancing. And in general, that's what we mean when we talk about robustness. It's defined formally in statistics concerning, extreme values, and that's pretty much how we're defining it here as well. A little bit more exacting with regard to this color balancing stuff. Okay, gradient boosting over traditional regression. Yeah, the gradient boosting over traditional regression. The gradient boosting is something that we can understand and look at the features, give the surgeons again those kind of things. And gradient boosting has the advantage that it's taking results from extreme points. It's taking these unusual points and it's learning from those. And whereas traditional regression doesn't do that, it's just it's a batch approach, and that's why it turned out gradient boosting was much more effective in this because it could learn that way. So that's the reason that it was used.
Well, with that, I want to thank you, Don, for giving us a fantastic overview on data science as a discipline, as a collaborative space, as a team sport, and some of the important elements that make up modern data science and as it applies to biomedicine. So thank you again. And I want to encourage all of you to join us once again next Friday at 12 noon Eastern Time and 9 a.m. Pacific for our next in the series of biomedical data science seminar series. So thank you once again, everybody. Have a great weekend.
Thank you. Bye-bye.